Fine. Let's start. Number 15. Flatland. Imagine you are a shape living on a tabletop. Not on top of the table. In it. You are a flat little triangle, and your whole universe is a smooth plane stretching out forever. You have left and right. You have forward and back. And that is all you have ever had. The word up means nothing to you. It isn't forbidden. It just isn't a direction your mind can hold. This is the world an English schoolmaster named Edwin Abbott built in 1884 in a strange little book called Flatland. And here's why we still talk about it. One day, into this flat world, a sphere passes through. A real, round, three-dimensional ball sinking through the plane like a coin dropping through the surface of a pond. Now think about what the flat creatures actually see. They can't see a sphere. They have no up to look along. All they can perceive is the slice of it that happens to be touching their plane at that instant. So first they see a single point that appears out of nowhere. Then a small circle. The circle grows, swells to full width, then shrinks back down, becomes a point again and vanishes. Something arrived from nowhere, changed size in a way no object should, and disappeared. To them, it looks like a miracle. To us, floating above, it's obvious. It was just a ball passing through. And that flips the whole thing around. Because now, ask the uncomfortable question. What would a four-dimensional visitor look like to us? By exactly the same logic, it would appear as a shape out of nowhere. It would swell and shrink in ways that break every rule of solid objects. And then it would blink out, gone, leaving us calling it impossible. No magic. No spirits. Just a cross-section of something too big for our senses to hold whole. Abbott's little square learns all this when the sphere lifts him up out of his plane and shows him his own world from above. And when he goes home and tries to tell everyone that a third direction exists, they lock him up for it. Which, if you know the history of people announcing new dimensions, is almost too on the nose. Flatland is a warning wrapped in a bedtime story. Our senses evolved to catch prey and dodge predators in 3 dimensions. They were never built to see everything that's there. And for one quiet moment, a flat creature saw a circle appear from nowhere and mistook a whole extra world for a ghost. Number 14. The Tesseract. Take a point, drag it, and you sweep out a line. Take that line and drag it sideways, and you get a square. Take the square and lift it, and you get a cube. Now do it one more time. Take the cube and drag it in a brand new direction, one perpendicular to all 3 you already have, and you get a tesseract. The 4-dimensional cube. That last sentence is easy to say and impossible to picture, and that's the whole point. You cannot draw a tesseract because your paper, your screen, and your visual cortex are all stuck in 3 dimensions or fewer, but you can do the next best thing. You can draw its shadow. Here's the trick. A cube is a 3-dimensional object, but it casts a 2-dimensional shadow on the wall, a flat outline of squares. In the same way, a tesseract casts a 3-dimensional shadow into our world. And that shadow is the image you have almost certainly seen. A small cube sitting inside a larger cube with slanted lines connecting the corners of one to the other. It looks like a box trapped inside a box. That picture is not the tesseract. It's the tesseract's shadow. The way your silhouette on the pavement is not you. This nested cube is just the trace of something rotating in a direction you can't follow. The name goes back to a thinker called Charles Howard Hinton in 1888, who was borderline obsessed with training the human mind to see the 4th dimension. He made colored cubes, memorized them, drilled himself for years, all to try to feel his way into that extra direction. Whether he ever really did is anyone's guess, and the tesseract has bled out of mathematics into art. Salvador Dali, in 1954, painted the cross in his crucifixion as an unfolded tesseract. 8 cubes arranged into a three-dimensional cross, a deliberate symbol of a higher reality intersecting our own. Count what it holds and the strangeness sharpens. A cube has 6 flat faces. A tesseract has 8 whole cubes as its sides, 24 square faces, 32 edges, 16 corners. Every one of those cubes is perfectly ordinary. It's only their arrangement, folded through the 4th dimension, that we can't hold in our heads. So when you look at that nested box and feel your brain refuse to lock it into place, that refusal is the honest response. You are staring at the shadow of a solid you were never equipped to see. And somewhere just off the edge of every direction you know, the real thing is quietly turning. Number 13. Fractal dimensions. Here is a question that sounds like it has a boring answer. How long is the coastline of Britain? Grab an atlas, run a ruler along the edge, and you'll get a number. But that number is a lie, and the reason it's a lie opens a door into a genuinely strange kind of geometry. Measure the coast with a ruler that's 100 kilometers long, and you skip over every bay and headland, and you get one length. Now, use a ruler 10 kilometers long. Suddenly you catch coves you missed before, and the coastline gets longer. Use a 1-meter ruler, and you start wrapping around individual rocks, and it gets longer again. Every time you look closer, more detail appears, and the length grows. There is no final answer. Zoom in forever, and the coastline tends toward infinite length, wrapped around a finite island. A mathematician named Benoit Mandelbrot took this seriously in 1967, in a paper with the wonderful title, How Long is the Coast of Britain? And his answer was that we were asking the wrong question. A coastline isn't really a line. A perfect line is one-dimensional, smooth, no detail hiding at smaller scales. A coastline has structure at every scale, all the way down. It's trying to be more than a line, but it never fills up a whole 2-dimensional area either. So it lives in between. Mandelbrot gave it a fractional dimension, a number that isn't a whole number. For the rugged west coast of Britain, that dimension comes out to about 1.25. Not 1. Not 2. 1 1/4. A shape that lives literally between the dimensions. And once you see it everywhere. A snowflake's edge. The branching of your lungs, which pack an enormous surface into a small chest by being roughly 2.9 dimensional. The forking of a lightning bolt. A head of broccoli. Mandelbrot coined the word fractal in 1975 for exactly these objects. Shapes whose dimension refuses to be a clean integer. Different coasts give different numbers. South Africa's smooth coast comes in around 1.02, barely more than a line. Britain's jagged one hits 1.25. The number is a measure of roughness, of how aggressively a shape crinkles into the space around it. This is the gentlest answer to our whole question, and maybe the most unsettling, because it's not hypothetical. It's not a theory waiting on a telescope. The space between 1 dimension and 2 is already occupied, and it's occupied by the shape of the ground where the sea meets the land. You've stood inside a fractional dimension. You just called it the beach. Number 12. Time, the 4th dimension. We keep hunting for extra dimensions out in exotic physics, in strings and brains and black holes, but there's one you're moving through right now, and you can't stop, and you can't steer. It's time. For most of history, space was space, and time was time. Two completely different things. Space was the stage. Time was the ticking clock in the corner. Then, in 1905, Einstein tangled them together, and 3 years later a mathematician named Hermann Minkowski made the tangling official. He showed that Einstein's relativity becomes clean and simple the moment you stop treating time as separate and start treating it as a 4th dimension, woven together with the 3 of space into a single fabric. Space-time. Minkowski said it with real drama back in 1908. Henceforth, he announced, space by itself and time by itself are doomed to fade away into mere shadows, and only a union of the two will preserve an independent reality. For a math lecture, that's practically a war cry. Here's the part that should stop you. In this picture, you are not sitting still. Nothing is. Everything is always moving through space-time at a single fixed speed, the speed of light. When you sit perfectly still in space, all of that motion is pointed in the time direction. You are, right now, plowing forward through the fourth dimension at the ultimate speed limit of the universe. When you get up and run, you steal a little of that motion and point it through space instead, which means slightly less of it goes through time. That is why a fast-moving clock ticks slow. It's not a trick. You're just spending your speed on a different axis. But time isn't quite like the other three, and there's one stubborn clue why. In the geometry of space-time, when you combine the directions, time enters with a minus sign, where space enters with a plus. That single minus sign is doing enormous work. It's the reason you can walk left and then right, back to where you started, but you cannot walk into yesterday. Space lets you turn around. Time, for reasons physics still argues about, only lets you go one way. So we live inside a four-dimensional block. Every moment of your life, birth to last breath, is already a fixed feature of it, like cities strung along a road. You experience it one slice at a time, always sliding forward, never able to face the other way. You didn't have to find this fourth dimension. You were never outside it. You've been falling through it since the day you started, and you will not stop until the day you do. Number 11. Phase space. There's a quiet myth that extra dimensions are the property of cutting-edge physics, something that showed up with string theory. That's wrong by about a century and a half. Physicists have been casually working in spaces of dozens, thousands, even trillions of dimensions since the 1800s. They just didn't make a fuss about it. Here's how it happens. Suppose you want to completely describe a single particle flying through the air. To know its state, you need its position, which is 3 numbers, 1 for each direction. But that's not enough to predict its future. You also need to know how it's moving, its momentum, which is another 3 numbers. So a full description of one particle takes 6 numbers. Now here's the move that changes everything. Instead of picturing those 6 numbers as position plus motion in ordinary space, treat them as a single point in a 6-dimensional space. 3 axes for where it is. 3 axes for how it's moving. Physicists call this phase space. One point in it captures the entire state of the particle, everything you need to know. As the particle flies, that single point traces a smooth curve through the 6-dimensional space, and that curve is the particle's whole story. One particle, 6 dimensions. Fine, but now do it for the air in the room around you. Every molecule needs its own 6 numbers. There are something like 10 to the 27th molecules in this room. So the phase space you'd need has over a billion dimensions. And the entire air in your room, every swirl and gust of it, is described by one single point moving through that unimaginable space. Sit with that. The air around you, in the mathematics that actually works, that engineers and physicists use every day, is a lone point drifting through a space with more dimensions than there are atoms in a galaxy. And it works. This isn't fringe speculation. This is the standard machinery of thermodynamics and mechanics, the stuff that designs your engines and predicts your weather. There's a cousin of this called configuration space, which drops the motion and keeps just the positions, and it shows up everywhere from robotics to chemistry. A folding protein, a walking robot, a planet's orbit, all of them get mapped as journeys through high-dimensional spaces that no one could ever picture. Now, a fair objection. These aren't extra rooms you could walk into. They're spaces of possibility, of information, a way of organizing everything a system could be doing. But that's exactly what makes them haunting. Long before anyone dreamed of hidden dimensions coiled in the vacuum, the most practical physics on Earth had quietly accepted that to describe the world, 3 dimensions were never going to be enough. Number 10. Hilbert space. If phase space felt like a stretch, quantum mechanics is about to take the roof off. Because the theory that underpins all of modern physics, the one that gives us transistors and lasers and the stability of atoms, does not do its business in ordinary 3-dimensional space at all. It plays out in a place called Hilbert space, and Hilbert space can have infinitely many dimensions. Let me try to make that concrete. In quantum mechanics, a particle doesn't have a definite position until you measure it. Before that, it's in a haze of possibilities. A bit here, a bit there, spread across every place it could be. To capture that haze, you need one number for every possible outcome. If a particle could be at any of 1,000 points, you need 1,000 numbers to describe its state, which is like a direction in a 1,000-dimensional space. But a particle can be anywhere along a continuous line, which is infinitely many points. So the space of its possible states has infinitely many dimensions. That state, that arrow pointing through infinite dimensional space, is the famous wave function. It contains everything the universe knows about the particle. And when you make a measurement, you essentially cast a shadow of that infinite dimensional arrow onto one particular axis, and that shadow is the result you read off your instrument. The rest of the arrow, all those other directions, collapses away. This structure was pinned down in the late 1920s and 30s, named after the mathematician David Hilbert, and built into quantum theory by John von Neumann. And it is not optional decoration. The infinite dimensionality is where quantum weirdness lives. Superposition, the ability of a particle to be in many states at once, is just the statement that its arrow can point in a combination of directions in Hilbert space. Entanglement, the spooky link between distant particles, is a geometric relationship in that same space. And here's the thing that should sit with you. Every prediction this theory makes has been confirmed over and over to more decimal places than almost anything in science. The machine you're watching this on is a monument to how right it is. So the most successful description of reality we have ever written describes everything. You, this room, the stars, as motion through a space with infinitely many directions. Not one of those directions is a direction you can point to. You can't turn toward them. You can't fall into them. And yet, the equations insist that's where the real action is, underneath the thin 3-dimensional surface we call the world. We keep asking what lies between the dimensions. Quantum mechanics answers with a shrug and an infinity, and then goes on being correct. Number 9. The 10 dimensions of string theory. Now we get to the theory that made extra dimensions famous. String theory started as a beautiful idea. What if the fundamental things in the universe aren't tiny points, but tiny vibrating strings, and every different particle is just a different note that a string can play? An electron is one vibration, a quark another, gravity itself another. One instrument, all of physics as its music. It's elegant. There's just one catch, and it's a big one. When you write down the equations and demand that they be mathematically consistent, that they don't spit out nonsensical infinities or negative probabilities, the math refuses to work in the 3 dimensions of space we see. It only works if space has more. For the version of the theory that includes matter as we know it, the superstring, the magic number is 9 dimensions of space, plus 1 of time, 10 in total. This isn't a preference. It isn't the theorists wanting more room to play. The number falls out of the requirement that a certain quantum inconsistency, called an anomaly, cancels out perfectly. It cancels in 10 dimensions and nowhere else. The universe, if string theory is right, is built on 10, and the equation simply will not close for any other count. So, where are the other 6? We look around and see 3. The answer string theory gives is that the extra 6 are compactified, curled up, rolled into shapes so unimaginably small, near a scale called the Planck length, about 10 to the minus 35 meters, that we could never notice them. Picture a garden hose seen from far away. It looks like a one-dimensional line. Walk up close, and you see it's actually a two-dimensional surface, with a tiny circle wrapped around at every point. String theory says space is like that everywhere. At every single point in the room around you, 6 extra dimensions are wound up too small to ever see. That's the part that gets me. The hidden dimensions, if they're real, are not far away in some distant corner of the cosmos. They're here, threaded through the air in front of your face, coiled up smaller than any particle we've ever detected, present at every point you occupy. I owe you the honesty, though. No experiment has ever seen a string, or an extra dimension, or the tiny curled-up shapes the theory needs. And the way those 6 dimensions can be folded isn't unique. There are an astronomical number of possible shapes, each giving a different physics, which makes the theory maddeningly hard to test. But the core claim stands as one of the most serious answers we have. Maybe the number 3 was never fundamental. Maybe it's just the count of dimensions, big enough for a creature our size to notice. Number 8. D-branes. If string theory says our universe has 10 dimensions and we only see 3, it raises an obvious, almost childlike question. Why us? Why are we stuck in this particular slice? Why don't we wander off into the others? In 1995, a physicist named Joseph Polchinski found an answer buried inside the theory's own math, and it reshaped the whole field. The answer is called a D-brane. To understand it, remember that strings come in 2 kinds. Some are closed loops, like tiny rubber bands. Others are open, like a piece of thread with 2 loose ends. And Polchinski asked a precise question. Those open string ends, what are they attached to? They can't just dangle in empty space. And the math replied that they end on surfaces, higher dimensional membranes, floating in the full 10-dimensional space. Those surfaces are D-branes. The D is for a boundary condition named after the mathematician Dirichlet. But forget the jargon. The picture is what matters. An open string is a thread with its endpoints glued down onto a sheet, free to wiggle, but not free to leave. Now here's the idea that turns this into a story about us. Suppose our entire universe, all the matter you've ever seen, every atom in your body, every star in the sky, is made of open strings, and all their endpoints are stuck to a single 3-dimensional brain sitting inside the larger 10-dimensional space. Then we would be trapped, not by walls, but by the simple fact that our strings are pinned in place. We could look in 3 directions and move in 3 directions, and the other dimensions would be right there, inches away in a sense, and we could never step into them. Light, made of open strings, couldn't leave the brain, so we could never even see out, with one crucial exception: gravity. Gravity, in string theory, is carried by closed strings, the little loops, and loops have no endpoints to pin down. So gravity is the one thing that can slip off the brain and drift into the full higher dimensional space. Which, if true, might explain a deep mystery: why gravity is so absurdly weak compared to the other forces. It's weak here because it's leaking away over there. Polchinski also showed that a stack of these branes behaves exactly like a black hole in higher dimensional gravity. That single realization lit the fuse for the holographic revolution we'll reach in a moment. So the answer to why us might be almost humbling. We are not the whole of reality. We might be a film of glued down strings on the surface of something vastly larger, pressing our hands against a wall we can't perceive, while gravity quietly walks through it. Number 7. Higher dimensional black holes. Here's a fact about our universe that's so familiar, we forget it's a rule. A black hole is a sphere. Its event horizon, the point of no return, is a smooth round surface. Every black hole we know, from the little ones to the monsters at the hearts of galaxies, wears the same shape. In 4-dimensional spacetime, 3 of space and 1 of time, it has been mathematically proven that a black hole's horizon has to be a sphere. It has no choice. Now add a dimension, just one. Go to 5-dimensional spacetime and ask the equations of general relativity what shapes a black hole can take. In 2002, 2 physicists, Roberto Emperon and Harvey Rial, worked it out, and the answer was jaw-dropping. In 5 dimensions, you can have a black hole shaped like a donut, a ring of darkness, spinning fast enough that it doesn't collapse, with a hole in the middle. They called it a black ring. Let that land. In our universe, that shape is forbidden. Gravity would never let a black hole be anything but a ball. But give space a single extra dimension, and suddenly gravity is happy to sculpt rings. And it doesn't stop there. Higher dimensions allow black strings, where the horizon stretches out into a long cylinder, an infinite pipe of darkness running off in a direction we don't have. And these exotic shapes behave in ways that would look like sorcery to us. A black string turns out to be unstable. Left alone, it does something eerie. It ripples along its length and beads up, like a stream of water from a tap breaking into droplets, pinching itself into a chain of separate black blobs. Gravity in higher dimensions has moods and behaviors that simply have no counterpart in our world. The deeper lesson is the one that should make you sit up. We tend to imagine extra dimensions as just more space, extra elbow room. But that's not what they are. Adding a dimension changes the laws of what can exist. It doesn't merely give gravity more room. It gives gravity new grammar. Objects that are logically impossible for us become routine 1 dimension up. So when you picture a 4th or 5th spatial dimension, don't picture an empty extension of the room you're in. Picture a place where the rules loosen, where the strict spherical tyranny that governs every black hole in our sky dissolves, and darkness is free to take shapes we have no words for. Rings, strings, chains of beads made of collapsed gravity. Our black holes are round because we live where they must be round. Somewhere with one more direction, the same physics dreams up monsters we could never build and calls them ordinary. Number 6. The Klein bottle. Let me hand you an object you can almost, but not quite, hold. Start with something familiar. A Mobius strip. Take a strip of paper, give it a half twist, tape the ends together, and you get a loop with a bizarre property. It has only one side. Run your finger along it, and you'll travel both faces of the original paper without ever lifting off. The inside and the outside have become the same surface. Now, a mathematician named Felix Klein asked, back in 1882, what happens if you take that idea up a level? Instead of a strip, take a tube, a bottle, bend it around, and instead of joining the ends the normal way, which would give you a donut, pass the neck of the bottle through its own side and connect it to the base from the inside. What you get is called a Klein bottle, and it is one of the strangest objects in all of mathematics. A Klein bottle has no inside and no outside. There is no boundary between in and out, because the surface flows continuously from what you'd call the inside to what you'd call the outside, without ever crossing an edge. Pour water into it, and there's a real question of where the water even is, because there is no enclosed in for it to be inside of. Here's the catch, and here's why it belongs in this list. A true Klein bottle cannot exist in 3 dimensions. Not without cheating. When you make one in glass, and people do, they're beautiful. The neck has to punch through the wall of the bottle, actually intersecting it, passing through the glass. That intersection is a flaw, a scar forced on the object, because our space is too small for it. The real Klein bottle, the perfect one, only exists cleanly if you have a 4th dimension to route that neck through, so it can reach the inside without ever touching the wall. It's the same lesson as the Mobius strip, lifted 1 floor up. A Mobius strip lives fine in our 3 dimensions. A Klein bottle needs 4 to be whole. And you can feel, holding the glass version, that you're looking at a compromise, a photograph of something that doesn't fit here. So the next time someone asks what an extra dimension would actually give you, you can hand them this. It would give a shape like the Klein bottle, somewhere to finally exist without wounding itself. A surface with no in and no out, seamless and whole, impossible in our world, ordinary in the next. We can only ever see its shadow, forced to pass through its own body, whispering that it belongs somewhere with a little more room. Number 5. The gravitational wave test. Everything so far has been theory and geometry. Beautiful, but you might be waiting for the obvious question. Can we actually test any of this? Can we look for extra dimensions, not with math, but with an experiment? The answer, astonishingly, is yes, and it involves catching 2 dead stars in the act of colliding. Here's the logic. Several theories of hidden dimensions predict that gravity can leak into them. Light can't. Light, in these pictures, stays stuck to our brain, our 3-dimensional slice. But gravity spills out. So if gravity leaks, then gravitational waves, the ripples in spacetime that spread out when massive objects crash together, should lose a little of their strength as they travel, bleeding energy into the extra dimensions along the way. They'd arrive at Earth weaker than they should be. And because we judge distance partly by strength, a weakened wave would make its source look farther away than it really is. That gives us a test. Find an event we can see 2 ways, once in gravitational waves and once in ordinary light. Measure the distance each way. If gravity has been leaking, the 2 distances won't match. The gravitational wave will say the source is farther than the light does. In 2017, the universe handed us exactly that event. 2 neutron stars spiraled together and collided, an event labeled GW 170817. Our detectors felt the gravitational waves shake spacetime, and telescopes around the world caught the flash of light from the same crash, pinned to a galaxy called NGC 4993. For the first time, we had 1 cosmic collision measured in both channels at once. So in 2018, a team of physicists did the comparison. They took the distance from the gravitational waves, took the distance from the light, and asked whether gravity had gone missing on the way. From that single event, they calculated the number of spacetime dimensions the waves had traveled through. The answer came back 3.98, give or take a little, which is, within the error, exactly 4. 3 of space, 1 of time. Precisely the number general relativity has always insisted on. No leakage, no missing gravity, no detectable extra dimension. Now, this doesn't slam every door. Dimensions that are curled up tiny, or that only bend gravity at very short range, would sail right past this test untouched. It only rules out the big, gravity-leaking kind. But think about what almost happened. For 1 measurement, across 130 million light-years, we could have caught gravity spilling out of our universe into somewhere else. We looked, and this time, The cosmos held its shape and kept its 4 dimensions to itself. Number 4. DGP gravity. There's a problem sitting at the center of cosmology that we've papered over with a name. The universe isn't just expanding, it's expanding faster and faster. Accelerating, as if something is pushing everything apart harder every year. We call that something dark energy. But naming a mystery isn't the same as solving it. We have almost no idea what dark energy actually is. So some physicists asked a heretical question. What if there is no dark energy at all? What if the acceleration is a symptom of something else entirely? Gravity quietly leaking out of our universe. In 2000, 3 physicists, Giadvali, Gregory Gabadadze, and Massimo Parati, built a model to explore exactly this. It's usually just called DGP, after their initials. The picture is this. Our whole universe is a 4-dimensional membrane, a brain, floating in a larger 5-dimensional space they call the bulk. All our matter, all our light, is confined to the brain. But gravity, once again, is the one thing that can seep off into that 5th dimension. The clever part is how the leaking depends on scale. Up close, at the size of planets and stars and galaxies, gravity stays trapped on the brain and behaves exactly the way Newton and Einstein say it should. That's why the model doesn't break the physics we've already tested. But at truly enormous distances, across the whole observable universe, gravity starts to slip away into the 5th dimension. And when gravity gets weaker at the largest scales, the universe's expansion is no longer being reined in as hard. Things drift apart faster. From inside, riding on the brain, it would look exactly like a mysterious repulsive force. It would look like dark energy, when really it's just gravity going missing next door. That's a stunning reframe. The single biggest component of the universe, the dark energy that makes up most of everything, might not be a substance at all. It might be an illusion, the visible side effect of gravity draining into a dimension we can't reach. I'll be straight with you about where this stands. The most exciting version of DGP, the self-accelerating one, has a technical sickness. It contains what physicists call a ghost, a sign of instability that makes the model probably unphysical in that form. And when you match DGP's predicted expansion history against the real data from supernovae and the cosmic microwave background, plain old dark energy still fits better. So DGP, in its boldest form, is likely not how our universe works. But it did something important. It proved that the acceleration of the entire cosmos could, in principle, be a leak. That the grandest mystery in the sky might be answered not by a new substance, but by a hidden door, and gravity slipping through it. Number 3. Twister space. So far, we've mostly been adding dimensions. More space, curled up, or leaking, or hidden. But there's a stranger possibility, one that comes from Roger Penrose, the same mind who won a Nobel Prize for his work on black holes. What if the problem isn't that we're missing some dimensions? What if space and time themselves aren't fundamental at all, and the real arena underneath is a different kind of space entirely? In 1967, Penrose proposed exactly that. He called it twister space. And the idea is genuinely dizzying, so let me build it slowly. In our ordinary world, the basic thing is a point, a location, here or there. Rays of light travel between points. Penrose flipped the hierarchy. In twister space, the fundamental objects are more like the light rays, and the points of our spacetime become secondary, derived things. And when you make that switch, the objects trade places in a very precise way. A single point in our spacetime, one location, one here, does not correspond to a point in twister space. It corresponds to an entire line. And a ray of light, which we think of as a long, extended thing, corresponds to a single point in twister space. What is a place for us is a line over there. What is a beam for us is a dot over there. The whole dictionary is inverted. Twistor space is a complex space built using imaginary numbers, and it has its own peculiar dimensionality that doesn't line up with our 3+1 at all. And the reason Penrose took this seriously, the reason it wasn't just a game, is that certain problems that are gnarly and tangled in ordinary spacetime become clean and simple when you translate them into twistor space. The equations for massless particles, for light itself, look far more natural there. For decades, a lot of physicists filed twistor theory under beautiful, but not obviously useful. Then, around 2013, it came roaring back. Nima Arkani Hamed and his collaborators found that if you use twistor methods, calculations of how particles scatter in collisions, the kind of thing done at the Large Hadron Collider, which normally take thousands of monstrous terms, collapse into a few elegant lines. The universe, at least in these calculations, seems to prefer the twistor description, which leaves us with a haunting thought. Maybe our spacetime, the here and now and the three directions you trust, is not the ground floor of reality. Maybe it's a projection, a shadow cast by a stranger complex space where the real bookkeeping happens, where your location is a line and light is a point. The between in this picture isn't a gap between dimensions. It's the deeper place our dimensions are drawn from. Number 2, the holographic boundary. Now we reach the idea that broke theoretical physics wide open, and it is so strange that when you first hear it correctly, it should feel like the floor tilting. It's called the holographic principle, and its sharpest form came from a physicist named Juan Maldacena in 1997. Start with a hologram, the ordinary kind, on a credit card. It's a flat, two-dimensional surface. But when light hits it right, you see a full three-dimensional image floating there, with depth, with sides, with a back. All the information needed to build that three-dimensional picture is stored on the flat, two-dimensional film. The depth is an illusion conjured from a surface. Maldacena proved that the universe can work the same way. He found a precise, exact mathematical equivalence between two completely different things. On one side, a three-dimensional volume of space with gravity inside it, with everything happening that happens in a universe. On the other side, a theory living only on the two-dimensional boundary of that space, the surface enclosing it, with no gravity at all. And here's the shock. These two descriptions are not similar. They are not approximations of each other. They are exactly the same physics, written two ways. Every event in the three-dimensional interior corresponds perfectly to something happening on the two-dimensional edge. The bulk and the boundary are the same reality. Think about what that implies. If everything happening in a volume of space can be captured completely by information painted on its lower dimensional surface, then, in a real sense, the interior, the depth, the extra dimension, is redundant. It's not adding anything the boundary didn't already contain. One of those two descriptions is not fundamental, and it might be the one with the extra dimension. It might be the depth. It might be the room you're sitting in. Maldacena's paper became the most cited work in the history of theoretical particle physics. Tens of thousands of physicists building on it, because it gave them a working example of quantum gravity they could actually calculate with. The extra dimension of space, in his model, emerges out of the physics on the boundary. Depth is the output, not the input. Now, the honest caveat. Maldacena's exact result works in a universe with a particular kind of curvature, called anti-de Sitter space, which is not quite the shape of our real expanding cosmos. Nobody has yet written the exact holographic dual of our actual universe, but almost no one now thinks the principle is a coincidence. The suspicion runs deep that reality, our reality, is in some sense a hologram, and the third dimension of the space around you is a story told by information living on a distant surface. The depth, may be the projection, and you are inside it. Number 1. Dimensions from entanglement. We've spent this whole journey asking what lies between the dimensions. Here, at the end, is the answer that reframes the question itself. Because the most radical idea in modern physics isn't that there are extra dimensions hiding between the ones we know. It's that the dimensions aren't fundamental at all. That space itself, and the very number of dimensions it has, is not a stage that things happen on, but something woven, stitched together out of something deeper. And the thread doing the stitching is quantum entanglement. Entanglement is the strange link between quantum particles, where two things, once connected, share a single joined state, no matter how far apart you carry them. Measure one, and you instantly know something about the other. Einstein hated it and called it spooky action at a distance. It's real. It's confirmed. And for decades, it looked like just another quantum oddity. Then, in 2010, a physicist named Mark van Ramsdonk asked a question so strange it had been sitting in plain sight. What is space actually made of? Working from the holographic ideas we just met, he ran a thought experiment. Take that boundary description of a universe and slowly dial down the entanglement between two halves of it. Just reduce the quantum connection between one region and another, and watch what happens to the space it describes. What happened was extraordinary. As he weakened the entanglement, the space in the interior stretched. The two regions drifted apart. And when he cut the entanglement completely, the space between them didn't just get long. It tore. It pinched off. The two parts of the universe pulled away from each other and severed, becoming two disconnected spaces. The entanglement wasn't happening inside the space. The entanglement was what held the space together. It was the fabric. Turn that around, and you get the deepest idea in this entire list. Space is connected and has the smooth, continuous shape it does, and the number of dimensions it does, because its underlying pieces are quantum entangled in just the right pattern. Geometry, distance, dimension itself are not the foundation. They are the shadow cast by quantum information. Weave the entanglement one way, and you get 3 dimensions. Weave it another way, and, in principle, you get something else entirely. So what lies between the dimensions? Maybe the honest answer is the loom, the place where dimensions are being made. Not a gap, not an empty corridor between floors, but the raw quantum threads that, knitted together, become the very idea of a floor, a direction, a distance, a here and a there. We started with a flat little square who couldn't imagine up. We end with the possibility that up and every other direction is being sewn into existence, right now, out of the entanglement of the world. The dimensions were never the bedrock. They were the tapestry. And somewhere underneath the smooth surface of the space you're sitting in, the threads are still being pulled tight. Thank you for watching and sticking till the end. We've got plenty more videos coming in the future. Hit that subscribe button so you don't miss them. See you in the next one.